We now have a basic understanding of wind direction around high and low pressure cells at the Earth's surface and at higher altitudes. These high and low pressure systems also have names. High pressure cells are called anticyclones, and low pressure cells are called cyclones. Let's review the diagrams you drew. You drew 6 diagrams, but on this page we have omitted the hypothetical pressure gradient only diagrams. So here, the top diagrams represent upper atmosphere flow, and the bottom diagrams represent surface winds. Now we know to call the high pressure cell diagrams on the left of this diagram here anticyclones, and the low pressure diagrams here represent cyclones. Let's review the diagrams. In a high pressure system, or an anticyclone, in the upper atmosphere, we're only dealing with the pressure gradient and the Coriolis effect, and the resulting winds are what we call clockwise geostrophic flow. Down closer to the surface of the Earth, friction is involved, which reduces the Coriolis effect, and essentially the pressure gradient overwhelms the Coriolis effect, and we have what's called divergent clockwise flow. There's still a clockwise nature to it, but the air is also diverging. In a low pressure cell or cyclone, we have in the upper atmosphere simply the pressure gradient and the Coriolis effect, and they balance each other out, and we end up with counterclockwise geostrophic flow. In the lower atmosphere, friction plays a role, the Coriolis effect is reduced, and we have still counterclockwise flow, but now since the pressure gradient overwhelms the Coriolis effect, we have counterclockwise convergent flow. When I was learning this material, I found it helpful to remember that in the cyclones, which start with a C, you have all the C words. It's convergent counterclockwise flow. A lot of C's. Thus far, we have focused on the northern hemisphere, and we will continue to do so. But the southern hemisphere flow patterns simply change the rotation direction. The upper atmosphere winds are still geostrophic, and the lower atmosphere winds are still divergent or convergent, depending on which type of pressure cell exists. Only the direction, clockwise or counterclockwise, changes. Next, we're going to add one more component to our model. We will add the vertical component within the center of the pressure cells. First, let's consider the high pressure system, the anticyclonic system. The air at the surface is diverging. But where does this diverging air come from? Air is entering from the center above. Thus, the vertical movement in the center of an anticyclone is downward. Notably, in the center of any pressure cell, high or low, there is very little horizontal air movement, very little wind. The primary motion in the center of one of these cells is down for anticyclones and up for cyclones. As we see here, in anticyclones, the cool air is descending in the middle and then diverging outward at the surface. This descending air actually helps create the high pressure. Also, importantly, next week we're going to learn that rising air is needed in order to form clouds. Thus, since anticyclones have descending air, they do not produce clouds or rain. Rather, as shown here, they are characterized by beautiful blue cloudless skies. Next, let's consider the low pressure system, the cyclones. Air is converging towards the center, but where does this converging air go? It has to go somewhere. air leaves the cell by rising upward. Thus, the vertical motion in a cyclone, in a low-pressure cell, is upward. Again, just like in high-pressure cells, the center of a low-pressure cell has little horizontal air movement, very little wind. The primary motion is upward for cyclones, just as it was downward for anticyclones. In cyclones, warm air is rising in the middle, and indeed this rising air helps create the low pressure. And since rising air is needed to form clouds, cyclones are excellent cloud producers and are characterized by cloudy skies. Indeed, that's another C we can add to our memory aid. Cyclones have counterclockwise convergent flow in the lower atmosphere, and then as the air rises, clouds form. Pause the video and talk your way through each of these diagrams again. In a low-pressure cell, or cyclone, air converges with counterclockwise rotation in the northern hemisphere, and the air rises to form clouds. In a high-pressure cell, or an anticyclone, the cool air descends and diverges, and the skies are clear. And in the northern hemisphere, that would be clockwise diverging air for the surface winds. One more time looking at a cyclone. At the surface, we have counterclockwise convergent air going towards the center. And in the center, we have rising air, which rises up to form clouds. In the upper atmosphere, we don't have the influence of friction, so the motion is counterclockwise geostrophic flow. In an anticyclone, we have air descending in the center, and that upper atmosphere air is moving clockwise in a geostrophic manner. As the air descends, it diverges outward for clockwise divergent flow. We don't expect there to be clouds in a high-pressure anticyclone because the air is descending. And in general, you need rising air to form clouds. Okay, now let's take it one step further. Where would you expect to find cyclonic airflow? At the equator or at the poles? How about anticyclonic airflow? Again, pause the video and think about that. Which one of these diagrams would be typical at the equator, and which one would be typical at the poles? Careful. Where would you expect rising air, and why would it rise? Okay, hopefully you said you would find a low-pressure cell, a cyclone, near the equator, and an anticyclone would be near the poles. Why? Well, near the equator, the air is warm, and the warm air expands, becomes less dense, and rises, thus forming a low-pressure cell and creating clouds. That fits nicely with our understanding from last week that the equatorial regions do not have the highest temperatures in the world due to frequent cloud cover. At the poles, the opposite is true. We have cool descending air forming a high-pressure system and clear skies. This diagram shows a low-pressure cell near the equator. The converging air rises and forms clouds. We'll see shortly that the rising air actually starts to move poleward at higher altitudes. And eventually, at approximately 30 degrees north and south, the air is cool enough that it starts to descend again, creating a high-pressure cell right around 30 degrees north and 30 degrees south. Indeed, right around 30 degrees north and 30 degrees south, there's a fairly consistent region of high pressure with cloudless skies. This is where we find the world's highest temperatures in the interiors of the continents. And additionally, because there are no clouds or very few clouds, this is also the location of many of the world's deserts. Pretty cool, eh? Check it out. Most of the world's deserts are somewhere near 30 degrees north or south. All right, let's use what we know about cyclones and anticyclones to determine if hurricanes are cyclones or anticyclones. Check out this remote-sensed image of Hurricane Katrina. Are the surface winds converging or diverging? Are the winds clockwise or counterclockwise? Pause the video and check it out. Hopefully, you said that the winds were converging and counterclockwise. That's correct. So does that make this a cyclone or an anticyclone? With convergent counterclockwise winds, indeed that makes this a cyclone. Actually, the clouds also give it away. What would an anticyclone look like on an aerial photo? You wouldn't see the rotation much at all, as there would be no clouds. Also consider what a hurricane would look like in the southern hemisphere. It would still have the cyclonic airflow, so still have the converging air that ascends in the middle. However, the direction would be different. In the southern hemisphere, cyclones, so hurricanes, would flow clockwise. Keeping that in mind, do you think hurricanes generally ever cross the equator? If the air flows clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, it seems unlikely that a hurricane could easily cross the equator. All right, so we now have a pretty good understanding of pressure and wind. We understand the three factors that affect wind direction, and we know something about both lower atmosphere and upper atmosphere winds in both high pressure and low pressure systems. Next, we're going to put all that together to develop a model for the Earth's general pressure and wind system to see the general airflow around the globe.